Well, this certainly seems like a natural stopping point. Just right there in the figure four. Somebody pointing at you like a punt gun. Um, for me, I'm going to be doing in India. Well, not, excuse me, not India. India is kind of in the middle of it. There's obviously 200 and some odd countries you got to do deals with. Who was who, what was what before an administration changeover. I hear Mexico is still a little frosty with it. But well, the lady president there, Trudeau is still Trudeau, but who knows? Mostly that's going to be the logging industry and any kind of mineral base that they have up inside of there. Start at the top here. Could throw that in. Want to stop with the dog and me for Schroestringer here because you'll see his work here in a second. There's one for Dirac. I'm gonna come in here just the audio, eating your vegetables on how to do the life or death uncertainty of quantum mechanics. This is the sun. It says sun. You click it, and then you get all these rays of sunshine and some of the core material sliding out. Which ones are heavy hitter pings on what it is. Shortest distance 21 feet, 21 centimeters, and depending on how old you are, somewhere between 21 and 30 centimeters from the heart to the brain and heart rate monitor. Of course, 21 centimeters of a hydrogen atom. Really important there. The number, wow, 10 to the negative 32nd, 34th. It's been a while since I played with it. Yeah, just roll up on somebody for what it does. Just bring it down because you're listening to Schroestringer's work, trying to rip it in here for the minutes on the system. And if you're not really paying attention to it, you might get clipped. You never know. That's just one of those things in the box while dealing with the Schroedinger equation. Some of the things in the box. Both of them. Right, you would think, the Coquel study, just to kick it in here for H wave function, the shortest distance, Planck's constant, I, and the derivative of a wave function. Kitties, this one, because they're the same thing, different. And that puts it in a box,
Hey, train plants every day.
Get some of that NP problem on this young lady right here being commander-chief of the bird there. So in the H function, as long as that's what it does, Jane Goodall, Schrodinger, Will on the model.
Equations in physics, the Schrodinger equation. It's an equation that lies at the heart of quantum mechanics, and it forms the basis of much of our modern understanding of the universe. But what exactly is the Schrodinger equation, and how can we use it to perform quantum mechanical calculations? In this video, I will provide an introductory overview of Schrodinger's equation, with my aim being that by the end, you should hopefully be ready to pick up an undergraduate textbook on quantum mechanics and actually enjoy the experience. So if you're up for the challenge, stay tuned. Our story begins in Vienna when on the 12th of August 1887, Erwin Rudolf Joseph Alexander Schrödinger was born. As was customary at the time, Schrödinger was educated at home for the first 11 years of his life before attending the local gymnasium
Any other
school.
song?
Almost from the very first day until he left 8 years later, Schrödinger excelled in mathematics and physics. When Schrödinger eventually arrived at the University of Vienna, much was expected of him, and he did not disappoint, consistently coming top of his class. His efforts were rewarded in 1910 when he received his doctorate, and after a short stint of military service, Schrödinger joined his old university as an assistant of experimental physics. In 1914, the First World War intervened, and soon after the war ended, Schrödinger took up a position at the University of Jena. The next 10 years saw Schrödinger move between numerous institutions in Europe before he finally settled in Zurich, Switzerland, at the age of 34. As the next few years passed, Schrödinger began to wonder if he would ever make a major contribution that would establish him among the first rank of contemporary physicists. At the beginning of 1925, he was 37 years old, long past his 30th birthday, which was believed by many to be the watershed in the creative life of a theoretical physicist. However, by the end of the same year, he would make a breakthrough that would ensure his place in the pantheon of physics.
Mario.
So what was it that suddenly changed the tide for Schrödinger? In October 1925, Schrödinger read a paper that Einstein had written earlier in the year relating to the latest developments in atomic physics. A footnote in Einstein's paper mentioned the thesis of a young French physicist named Louis de Broglie, who had recently published his thesis on the theory of wave-particle duality a few years earlier. This rather innocent footnote caught the attention of Schrödinger, and he set about acquiring a copy of de Broglie's thesis. What was particularly exciting for Schrödinger was that de Broglie had dared to ask the question that if light waves can behave like particles, as has been shown by Einstein's explanation of the photoelectric effect, is it then possible that particles such as electrons can behave like waves? De Broglie's answer to this question was an unequivocal yes. In summary, de Broglie proposed that for a matter particle with mass m moving at velocity v, you can associate a plane wave of wavelength lambda equals h over p, or h over mv, where p equals mv is the momentum of the particle, and h is Planck's constant. Furthermore, if the particle has energy E, then you can assign a frequency given by F equals E over h, and these relations connect the particle concepts of energy and momentum, E and P, with the wave concepts of frequency and wavelength, F and lambda. Now what de Broglie did was simply assume that these two relationships hold for all matter particles, including electrons. Although there was no experimental evidence at the time to support de Broglie's hypothesis, he was encouraged by the fact that he was able to provide an explanation for Bohr's model of the atom. Although other physicists had taken a passing interest in de Broglie's work, the lack of experimental evidence dissuaded most from spending too much time thinking about the ideas. However, when Schrödinger read de Broglie's paper, he immediately wrote to Einstein to share his thoughts about the implications of wave-particle duality. A couple of weeks later, Schrödinger was asked by the physicist Peter Debye to present a talk on de Broglie's work at a physics colloquium in Zurich. Schrödinger gave a beautifully clear account of de Broglie's work. However, not everyone in the audience was convinced. In particular, Peter Debye did not like the fact that according to de Broglie's theory, there appeared to be matter waves, but no wave equation to describe these waves. How can you have a wave without a wave equation? According to the well-established classical laws of wave motion, any wave, whether it's a sound wave, electromagnetic wave, or wave on a vibrating violin string, has an equation that describes its motion. However, in de Broglie's theory, there was no wave equation. De Broglie had never attempted to derive one, and neither had Einstein. Schrödinger knew at once that Debye was correct. You cannot have waves without a wave equation, and almost at once he decided to set himself the task of finding the missing equation. And in the space of only a few months, Schrödinger was able to take de Broglie's tentative ideas surrounding wave-particle duality and develop them into a fully blown theory of quantum mechanics. In the remainder of this video, I would like to provide a simplified overview of Schrödinger's theory. We will begin our investigation with a simple review of the properties of classical waves. A simple progressive wave which is moving towards the right can be described using a cosine function, where y of xt is the displacement at position x and time t, and a is the amplitude or maximum displacement of the wave. In this expression, we have defined the wave number k as 2 pi over lambda, where lambda is the wavelength, and we've also defined the angular frequency omega as 2 pi f, where f is the frequency of oscillation or vibration of the wave. Now, this displacement function is a solution to a general wave equation which takes the following form. It's worth noting that this equation involves partial derivatives, which are represented by the curly d symbol. In the wave equation, the displacement function y is a function of two variables, x and t, and so it's appropriate to use the partial derivative symbol when differentiating with respect to one of the variables. We can confirm that the cosine wave function is indeed a solution to this wave equation by substituting it into the equation. If we take the first and second derivative of the wave displacement relation with respect to time and space, we get the following relations. And then if we sub these back into the wave equation, we find the following green expression. If we then divide both sides by y, we find that v squared equals omega squared over k squared.
You have
And therefore we see that this displacement
James
function
model,
is indeed
SAT.
a solution
You
to the wave equation,
have the
provided
dyslexic
that v
kid and
equals omega
Galatian
over
book
k.
guys, bell tower ones.
If we
there.
then substitute in the
And then you
definitions
have
of
just
omega and
this.
k, we
This-
see that this constraint is none other than the famous velocity, frequency and wavelength relation v equals f lambda.
Careful.
Now, it's worth emphasizing a few points at this stage. We see that the structure of the wave equation has ensured that the expected wave function is indeed a solution, and it's also ensured that we arrive at the correct relationship between velocity, frequency and wavelength. This can ultimately be traced back to the fact that when we differentiated twice with respect to space, we got a factor of k squared, and when we differentiated twice with respect to time, we got a factor of omega squared, and therefore we found that v squared equals omega squared over k squared, from which it followed that v equals f lambda. And so to summarize, we have seen that a wave function is a solution to a wave equation, provided that a certain relationship between frequency and wavelength holds true. And for the classical wave we've considered, this relationship between wavelength and frequency is precisely what we expect for a travelling wave. And it was this relationship between wave function and wave equation that Schrödinger started thinking about in 1925. If de Broglie was correct, and particles behave like waves, then these de Broglie wave functions should be solutions to a wave equation. If so, what form should this wave equation take? Would it have the same form as the classical wave equation we've just seen? And if not, why not? Now, if a freely moving particle is to be described by an associated wave, then a reasonable first guess would be to suggest that the wave is described by a progressive travelling wave, which, as we've already seen, can be described by the following function. This makes sense as a first guess, since this function describes a wave with fixed frequency and wavelength, and according to the Einstein-de Broglie relations, if the wavelength and frequency is constant, then so is the momentum and energy, as would be expected for a freely moving particle. However, if a force were to act upon the particle, then according to Newton's second law, the particle's momentum would change, and therefore, according to the de Broglie postulate lambda equals h over p, the wavelength associated with the particle will also change. However, the concept of wavelength is not well defined if it changes very rapidly. It's difficult to define even a variable wavelength, since the separation between adjacent maxima is not equal to the separation between adjacent minima. To put this another way, if the linear momentum of a particle is not of constant magnitude because the particle is acted on by a force, then functions which are more complicated than a cos kx minus omega t are required to describe the associated wave. The challenge facing Schrödinger was to develop a wave equation that could determine the wave function for any given situation. In other words, Schrödinger wanted to develop a wave equation